In this video we're going to introduce the concept of mutual inductance or coupling, where energy from one coil is coupled through the magnetic field into a neighboring coil. Now, as we have discussed, when a current is flowing in a coil of wire, there is a magnetic field induced that is oriented along the length of the coil. When that current is changing, there is also a voltage that is induced across those coils. Now, when another coil is brought into proximity of the first coil and its changing magnetic field, a voltage is induced in the second coil. As we saw, the voltage in the first coil was equal to this constant that was associated with the physical structure of the coil, which is known as its inductance, times the derivative of the current flowing in there. It turns out there's a similar relationship to the voltage induced in this secondary coil. The voltage here is equal to some constant M times the derivative of the current flowing in the first coil. This constant M is known as the mutual inductance. M is the mutual inductance of the two coils next to each other, where M is equal to some constant K times the square root of L1 times L2, where L1 is the inductance of the first coil, L2 is the inductance of the second coil. So this mutual inductance is proportional to the square root of the product of those two inductances. This constant K is known as the coefficient of coupling, and it's a value that runs from 0 to 1, where a value of 0 means that there is no coupling between the two coils, and a constant, or K equaling 1, means that there's perfect coupling. In other words, the entire magnetic field induced by the first coil is completely coupled by the second. In both instances, the voltage induced in the primary coil due to the current of the primary coil and the voltage induced in the second coil due to the currents in the first coil only exist, these voltages only exist if the current is changing. Both of these voltages are proportional to the derivative of the current with respect to time. Let's now look at this with a little bit more detail. We have here a current, or a circuit, consisting of a coil being driven by a source here that's causing a current I1 to flow into this terminal. Nearby, in proximity of this coil, there is another coil that is mutually coupled to this coil here through the magnetic field, and it is driving a second resistor, R2. In this configuration, then, we have two currents flowing. One current flowing in the left-hand loop, and I've referenced it into the terminal here, and the second current, which is induced by the current in the first, but a current nonetheless that's flowing, and I've referenced it into this top terminal like this, I1 and I2. Each of these currents flowing through the coil will induce a voltage across each of their own coils that is proportional to the derivative of the current. In other words, you'll have a voltage across here, V is equal to L1 dI1 dt, and there will be another voltage here. There will be another voltage here induced with V equaling L2 dI2 dt. These two voltages are referred to as the self-induced voltages. They're referenced so that the current flowing, I1, flows into the positively referenced terminal of this voltage, and I2 is flowing into the positively referenced voltage there. In addition to these self-induced voltages, there's also, or each of these currents also induces a mutually induced voltage, or induces a voltage in the other coil. So, I1, in addition to the self-induced voltage in coil 1, I1 also induces a voltage in the neighboring coil. Similarly, the current that's flowing through L2 induces not just the voltage in L2, but also the voltage induces a voltage in the neighboring coil there. These are known as mutually induced voltages. Now, because the direction of the B field of the magnetic field established by I1 is dependent upon how the coil is wound and the direction of the current is flowing through it, the polarity of these two voltages requires some additional attention. There's a convention that has been developed to mark the coils to communicate this information, or this polarity information, on a schematic drawing, because it's awfully difficult to tell just by looking at a schematic symbol for these inductors which way they're coiled and which direction the magnetic field will be induced. So the convention is that one terminal of each coil is marked with a dot, such that the voltage that is induced by a current flowing into the dot on this coil will induce a voltage that is positively referenced at the dotted terminal of the other coil. Thus, I1 is referenced into the dotted terminal. It's going to induce a voltage in the other terminal which will be referenced with a positive reference at the dotted terminal of the other. So this then would be M, the mutual inductance, times dI1 dt. So there's another voltage here. It's the voltage in coil 2 due to the current 1 that is created through this mutual inductance. Because I1 is referenced into the dot, the voltage due to that current will be referenced positively at the dot. On the other hand, I2 is referenced into the terminal not containing the dot. It's referenced into the undotted terminal. So the voltage that this current induces in the neighboring coil due to the mutual inductance will be referenced positive at the undotted terminal. And we'll have a voltage plus to minus here then that is equal to M, the mutual inductance, times the derivative of the second current with respect to time. So to restate this in a little bit of review, each of these coils has two different components of voltage. There's just one overall voltage, but it consists of two components. One component due to the self-induction of the current flowing through this inductor, L1 dI1 dt, and the other component of the voltage across this coil is due to the current flowing in the other coil that mutually induces a voltage in the first coil. And the voltage here in this first coil is proportional to the derivative of the current flowing in this coil. Similarly over here, there are two components to the voltage across this coil. One component is due to the current flowing through here, L2 times dI2 dt, and the other component is due to the current flowing in the other coil that is mutually connected, or magnetically connected between the two. In the next video, we'll go into the details as to how we determine which of the terminals receive the dot markings.